All right. So our second speaker is Zhenbin Yang from Institute for Advanced Study and Tsinghua University. And he will talk comments on the de-Sitter double cone. Let's welcome the speaker.
Okay. Tau 0 is the initial time of the clock. So in particular, this clock here. Well, I'll talk about what is the model of the clock. So tau 0 is the initial time of the clock. Right? Because the clock can evolve from any initial time, and so that is the overall zero mode. We will strip that out. Further question? Yeah. So in this model, you have ideal clock. Then you imagine the range of the clock time is infinity. So such that you can faithfully keep track of the time. Yes, this one is the same. The clock is another name for time, and here by observer, I mean I'll discuss what observer means. Observer means the clock and also keep track of its location in de Sitter space. So it will be the observer will be modeled by a clock union observer. A clock union particle. Observer will be a clock union relativity particle. Okay. So I was talking about that the CFPW paper showed that the algebra of a static patch is type 2-1, and then for a type 2-1 von Neumann algebra, you can define the von Neumann entropy, and by calculating the von Neumann entropy for a geometry where you have a de Sitter and in perturbative matter, CFPW showed that the entropy difference is given by this generalized entropy of de Sitter static patch. So that contains the area of the de Sitter horizon plus possible matter entropy inside of the patch. Being a type 2-1 von Neumann algebra, that means the vacuum de Sitter have infinite temperature. Last December, Juan Madacena demonstrated that instead of using von Neumann algebra, you can use a tool of a gravitational path integral while including the observer. Then he showed that the Sophia patching function can be interpreted similarly as a continuum of the Hilbert space up to a minus sign. Here, the putable Hilbert space of a static patch is thought of, we think of the putable Hilbert space as a union of the observer Hilbert space and some de Sitter Hilbert space, subject to the Hamiltonian constraint because the whole system is closed. So this H means the total energy of the static patch that include the some putable energy of the de Sitter patch, and then the energy of the observer. So and the physical Hilbert space will be given by the union of this with imposed Hamiltonian constraint. Then Juan argued that if you consider the Euclidean Sophia patching function that includes the pure Einstein gravity term times the observer term, then the Sophia patching function can be interpreted as a trace 1 in the physical Hilbert space. So before you, maybe let me spend a few words about the formula. So before you're introducing the observer and only consider the Sophia patching function in GR, then Joe Polchinski famously found that this patching function is not real, positive, due to conformal modes. So if you look at the scale factor, then you find the Euclidean patching function around the Sophia have the scale factor have a negative mode, and so you have to do a contour rotation But then on sphere, you have this conformal killing vector, which is just diffeomorphism. So you're not supposed to, you are supposed to gauge it out, not supposed to integrate out. So that gives you a few modes left that you won't rotate it. This conformal killing mode and another overall scale that leads to a phases. It's I to the d plus 2 for d-dimensional sphere. And what Huang showed is that now if we consider including an observer, then the observer also contains some phases because the observer trajectory is also unstable under the perturbation. So that cancels most of the i's, but in the end left three negative modes. There are three negative modes left, so that gives you this minus I factor. Yeah. If you have multiple observers, you have multiple eyes, then those have physical interpretation corresponding to, with respect to a single observer, the other observer are unstable. They will decay into static patch. Yes. You can also have some other field that is unstable. Those will also give you eyes. But those we think are physical instabilities with respect to choosing observer. No, 3 is related to something else. I'll tell you one. I'll tell you one of the three, and the second two is still undergoing. I'll not tell you what are the. Well, I can tell you what are the next the other two, but the physics is understanding its physics is still not clear. So let's go. Let's talk about the single factor of I. So there's a. So yeah. So you find the sphere patching function as I to the cube. The 3 is 1 plus 2. Okay. This 1 comes from the L equal to 0 mode of the scale factor, and that you can understand as coming from the is related to the inverse temperature of the system. And Huang argued that this factor of I can be understood as a difference in the measure between the Euclidean path integral and the inverse Laplace transformation used to impose the Hamiltonian constraint. So that gets rid of one of the I. And then the rest minus signs remain unexplained. So this factor 2 I didn't explain. And in our work, we assume this minus sign do not invalidate the big counting interpretation. But you should keep that in mind. Okay, maybe let me say a few more. What is this rest factor minus sign corresponding to? So if you think about the conformal killing vector on the sphere, so you can think about d-dimensional sphere. You can embed it as a right. So the conformal killing vector will move the d-dimensional sphere in various ways. When you're including observer, most of these conformal killing modes will move the observer. So when you're including the back reaction of the observer, it stabilizes those negative modes. But now, if you consider, then there's two conformal killing modes that makes the observer trajectory fixed. So those two conformal killing vectors are the rest factor 2. Okay. Yeah. Okay. Well, because it's a closed system, so we do not fixing any. We do not fix the temperature around the observer. We do not fix the inverse temperature around the observer. So the observer trajectory could arbitrate size. Yeah. Yeah. Yes. Then it looks like cannot have any phases, right? No, so if you do that, you use the reflection positivity, then you find the actual answer divergent because those instabilities. So now what you do is you slightly change the problem by adding I epsilon in the Newton constant. So that rotates those unstable modes, but it's not overall field redefinition because of this conformal mode. So that gives you some factor of i's. And the point is that after you introduce observer, then there's two residual conformal Killing modes that still gauge symmetry. So that's the overall minus sign. Okay. But let's set that aside. Maybe that will change our interpretation of what is static patch de Sitter holograph means. But for our purpose, let's just assume this minus sign does not change the whole story. And we want to examine the effect of the Hamiltonian constraint on the clock system. More precisely, we want to calculate the return amplitude and the return probability. Those two quantities do not necessarily to be equal to the square of the other because we learned in JT gravity and other point models that sometimes simple gravity may calculate ensemble average of theory. So for the return amplitude, we are computing path integral over all closed manifold containing a single observer whose time runs from 0 to t. And for the return probability, then we're computing sum over closed manifold, including two observers whose clock runs from 0 to t and 0 to minus t. So in particular, in this work, the geometry contributed to this return amplitude will be a sphere, including observer. And then the geometry contributed to the return probability will have square of the sphere, but also a double cone geometry that I will explain. So now let's go to the observer model. Here we take the observer model as a consists two parts. One is a relativistic particle moving in d-dimensional de Sitter space, and a free clock that measures a particle's proper time. So this is a relativistic particle action, and the clock contains T and E, where E is the energy and T just labels the time of the clock. And because this observer is moving in a closed universe, we can do a gauge transformation, do an isometric transformation of a de Sitter that maps the physical configuration invariant. So we should, in addition, gauge out the de Sitter isometries. So that's the observer model. But for now, let's first set the gauge symmetry aside and just consider simply this relativity particle plus clock action. So we can consider, for example, it's Euclidean propagator from x0 to x1, where the clock runs from 0 to t, curly t. So now we do this path integral. It consists three parts. First is the trajectory of the observer of the particle. It's a map from 0, 1 to s to an interval to a d-dimensional sphere. Then the clock path, we're conditioning that the time should flow forward. So that becomes a sum of monotonic maps from interval to interval. And third, we should gauge out the reparametrization symmetry, which is a diff interval. We can gauge fix the reparametrization. Yeah. Here we take it from minus infinity to infinity. Well, you will find later on it will become zero. So let's first gauge fix the reparametrization symmetry by fixing the clock path. That's what you can do. Then you do the integral of the clock energy that enforces the proper time constraint. That just tells you that you can always parameterize your trajectory using the clock variable. So, so now this path integral just reduces, sorry, this is a typo, reduces to sum of all paths with fixed proper length on the sphere. At microscopic level, summing over such random passes is just nothing but Brownian motion with a Hausdorff dimension 2. That means in the continuous limit, this reduces, I don't know why, reduces to a non-relativity particle action moving on SD with the standard non-relativity action. So we see that after this manipulation, we find the observer model is nothing but a nonlinear signal model whose target space mapped from an interval to a SD, or under another continuation, it's a DSD. It's somehow reminiscent of the hydrodynamic approach to black hole thermodynamics, where you have a physical spacetime and a box spacetime, where the box spacetime is kind of a fluid spacetime. Okay. Now, recall that we are parameterizing the non-relativity particle time with the clock time. So the energy of this non-relativity particle is nothing but the clock energy. So also recall that if you consider the phase space of a relativity particle in SD, DSD, so it's 2D minus 2. But a non-relative particle in DSD, it's a phase space of 2D. It's actually 2 coming from the 2 phase space of the clock. Next, we want to impose a gauge constraint. So we start with the Hilbert space of this non-relative particle, but now we have to impose the de Sitter isometry. So we need to quotient out the SOD, 1. This is a non-compact group, and gauging such a G requires the use of something called co-invariant Hilbert space. It consists of 2 steps. The first step is to define an equivalency relation in the original Hilbert space. You define 2 states are equivalent if they differ by action of a gauge transformation. And second is that you need to modify the inner product. So the modified inner product is related to the original inner product by a group average of your SOD, 1. So now, so that defines the co-invariant Hilbert space. So for this case, let's now, from now on, let's focus on the Lorentzian case. So we have a de Sitter space. So in order to satisfy the constraint, you have to have 2 observers that carry energy sitting in the static, opposite static patch. So, so to look at its co-invariant Hilbert space, you can just find a representative in each of the equivalence class. In particular, we are fixing the gauge in the following way. So first, you can fix the left observer at the north pole of the spatial sphere at t equal to 0. So you can always do it, and you can always fix that using the de Sitter isometry. So after that, you have a residual gauge symmetry is SOD minus 1, 1. And that have multiple orbits in the Penrose diagram of a de Sitter space. It turns out that only if the observer is sitting in the another static patch, it will satisfy the constraint. Satisfy the constraint. So that you can always bring the right observer, fix it at the center of the opposite static patch. So the only physical degree of freedom left is a relative time shift between the 2 observers. And furthermore, you can gauge out the time refraction symmetry to constrain T to be positive. So that tells you that the co-invariant Hilbert space of this observer model is L2 of R+. You can also work out the Hamiltonian acting on this co-invariant Hilbert space. Then you find it takes the following form. And the boundary condition is that it has to be smooth at t equal to infinity and smooth at t equal to 0. And you can also work out the inner product using the group average formula. So for d-dimensional de Sitter space, the inner product is the following form. So you can also work out the eigen system of this co-invariant Hilbert space. And here you find the energy is bounded from below, okay, the clock energy. And this is the wave function. It satisfies a standard orthogonal relation and yeah, etc. This will not be important for the later part of the talk. So now let's use this Hilbert space of observer trying to calculate the return amplitude and the return probability. So for example, for the return amplitude, we will consider the Saphir-Pachin function with the observer whose clock runs from 0 to t. So up to the so for the observer model, we can view this Saphir-Pachin function as the inner product of the two Hartree-Hawking wave function, which we can expand it in terms of the energy basis S. And the return amplitude is nothing but just the return amplitude of the Hartree-Hawking wave function under the clock time t. And if you plug that in, you indeed find it's proportional to a dead function in the limit when the mass of the observer is heavy. Now let's go to the non-perturbative contribution. But are there any questions at this step? Oh yeah, it it is which eye? Oh, this minus sign. Yeah. So we are doing so we do the gravitational path integral and the observer path integral step by step. We first do the gravitational path integral, so that fixes the overall thing, and then we ask the observer whose clock runs from there to t. So that I'm doing the second step. The first step is just a conventional Saphir-Pachin function. So that gives you this minus I. Okay, now let's go to this go to this double cone contribution. So again, the philosophy is that we first do the gravitational path integral. So that means we first need to find the classical saddle of Einstein-Hilbert action that can support two closed time-like geodesics. And here is the universal construction. So start with a static patch of de Sitter space. It has a boost killing vector. So you can take a quotient of the boost killing vector with amount t to generate wormhole geometry. Such a quotient will satisfy the Einstein equation everywhere except near the at the tip of the horizon. That you need that requires an I epsilon description. And that's a standard trick for the double cone geometry that you deform the radial contour instead of from minus infinity to plus infinity, but slightly deform it through the lower half plane, imaginary half plane. So more concretely, the metric of the de Sitter double cone is given by the following metric. The I epsilon description makes the geometry smooth everywhere. Okay. Let's make a few comments about this wormhole geometry. This double cone construction, as I said, is universal for any killing horizon. Because the universal near horizon render structure. For any geometry with a killing horizon, when close to the render, close to the bifurcation center, you'll find the render structure, and then you can deform the radial contour through the lower half plane. And that explains why it applies both to the black hole and de Sitter horizons. And historically, this double cone geometry is first discovered by Sashek and Stanford in the context of the black hole thermodynamics. Second property is that the physical quantity derived from this geometry is independent of the specific value of epsilon because of analyticity property. And the last point I already mentioned is that such a double cone contains two close time-like geodesics where you can put the clock in, and that serves as a connected geometry contribution to the return probability of the system. You can calculate the on-shell action of this wormhole geometry, then you find it vanishes. That means it's e to the minus 2 times the entropy of 2 times de Sitter entropy suppressed relative to the Saphir-Pacheco function. And then the path integral then just reduces to the one loop determinants. So if we have a matter observer, then it reduces our graviton, then you are calculating the one loop determinant on this double cone geometry. And that will be our next goal. A third comment is that there exists a larger family of double cone geometry in de Sitter space. Namely, you can consider Schwarzschild de Sitter geometry, which also contains a Killing vector. You can take quotient. Now, this geometry have a topology of T2 cross S2, where S2 is the transverse direction. However, we think such contribution will decay at a late time. So now, let's first talk about the matter patching function. Recall that the double cone geometry have a topology of S1 cross SD. So if you consider the one loop matter patching function, that can be thought of as evaluating a bulk trace over the matter Hilbert space in de Sitter space. And in particular, this one loop patching function can be rewritten as a trace of the evolution operator of this modified boost operator. Here, K is a boost operator acting on the matter field associated with the de Sitter horizon, and H is a Hamiltonian defined locally at the horizon. This IF modification is due to the IF deformation I introduced for the double cone. And you can calculate the spectrum of this modified boost operator. Then you find it is given by the quasi-normal frequency of this sum of your double geometry. And in particular, in this double cone geometry, you this is general. You just sum over all the quasi-normal modes will give you this infinite product of the trace. And for this de Sitter case, all the quasi-normal all these quantities decays when t is bigger than the Hubble radius. And such a time when the matter field on the double cone decays to 0, in the case of quantum chaos, define something called the Thoris time. And here we find that the Thoris time is equal to the Hubble time. Yeah. Yeah. So locally, you have a Rinder horizon, right? So it's locally flat. So you can H is defined as a global time translation at near the Rinder region. No, it's not a boost. It's a so any linear horizon, locally it's flat, and H acts as a global time translation of the linear horizon. So in general, it's not a symmetry, the Minkowski time. In general, it's not a symmetry, but it's an approximate symmetry near the horizon, and that's all you need to define this modified boost operator. Okay. So why the spectrum of the K tutor is given by the polynomial modes? Here, let me just illustrate the idea using a simple example of a scalar field phi. So we can examine this behavior of the scalar field near the horizon. Then the transverse direction, you can always do a Fourier decomposition of the transverse direction. So effectively, what's important is this radial and time direction, and these two components. And so you can solve the solution of the Klein-Gordon equation you find given by these two two solutions. Here, this k is the eigenvalue for the modified boost operator partial t, and we need to determine what's the value of k. T is time conjugate to k tilde. Yeah, the boost. Yeah. So because we introduced the Epson description, so the solution we need to be smooth cross analytic continuation of the row from the static patch to another static patch from the left to right. So that analytic continuation continue row to e to the minus I pi row. So that introduces some extra factor in front of the ratio of these two unknown constants. But once you impose the boundary condition in here, it's a smooth boundary condition at the center of the static patch. The ratio is fixed. So in order to be consistent, that requires either AK or BK to vanish. That defines ingoing or outgoing boundary condition for the static patch. And because this boost operator k tilde, oh, sorry, something I forgot to mention is that because this Epson description, this k tilde is a non-Hermitian operator. And in particular, this H as a global Hamiltonian as a Minkowski Hamiltonian is positive definitely defined. That tells you that k tilde should have a negative imaginary part. So using that property, you can rule out the outgoing boundary condition, and that gives you that the spectrum of k is given by the quasi-normal frequency. Next, we'll talk about the matter patching function. So similarly, for the matter part, you can also calculate as evaluating a bulk trace naively, but recall that the observer Hilbert space is invariant under the de Sitter isometry. So that reduces trace of 1. So you get the integral over the whole Hilbert space. But now recall that the t variable is a bulk time. And on the double cone, we are compactifying the bulk time. So the range of t is compactified to the range to the period of the double cone, which is denoted as capital T. So that tells you this result of this double cone patching function have a linear integrals. And the range of the double cone will be fixed to be equal to the clock time with the curly T when the observer is heavy. Yeah. Yeah, this T is a compactifying time. So I compactify the static patch de Sitter by boost amount with total amount capital T. So that's a period of the double cone. So recall that the double cone is obtained by quotient with a boost evolution operator with amount T, e to the I k T. So this capital T is a parameter of the double cone. The little t is a coordinate time. Is this little t? Yeah, this little t, recall that is a relative time shift between the two observers. So there's two observers, they differ by this little. Oh yeah, sorry. You mean what's the relation between this little t? Yeah, they're not the same. Yeah, sorry. But okay, this perhaps this derivation is a little bit too fishy. So I try to do a better job by considering the direct path integral for the observer on the double cone. Daniel, you have a question? So, so now let's try to directly computing the path integral of the observer model on this double cone. So recall that the observer model is given by this nonlinear signal model. So here it's a one-dimensional nonlinear signal model whose target space is this double cone. So we're summing over all the passes with this action. And this bulk time, little t, is periodically identified because of quotient. And furthermore, we have to quotient a residual U1 isometry of the double cone. So you can do this path integral. So the saddle point is given by a static trajectory at the center of the static patch. Because the left-right action is the same, so let's just focus on the left. So now we can do a perturbation around this classical saddle. So by working out to the perturbation, you find as a following action, quadratic action. Here, epsilon is a fluctuation of this bulk time t, and xi is a transverse fluctuation of the particle. So if you do this epsilon integral, you find this this one loop term, and the xi integral give you one of the singe. That tells you nothing but the particle is unstable in the de Sitter. Just de Sitter is expanding. So if we put the left and right observer together and quotient the U1, so that get rid of this t one factor of t. So that gives you this action, this quantity, this Pachin function. Now we need to sum over all the double cone geometries, where this mu of t is some unknown measure associated with the integration of the double cone. So our next job is to determine this mu of t. The curly t is a clock time. So yeah, so the observer now it's reduced to a 1D nonlinear signal model. So here it's from S1 mapped to the double cone. This curly t is a period of the S1. Okay. U. Yeah, U. Yeah, curly t is the period of U. Okay. Yeah. Okay. So recall that we obtained the double cone by taking a trace of isometry in the of the de Sitter of DSD, and in principle we can construct a family of double cone geometry by tracing over each conjugate element that lies in the conjugacy class of this boost operator. But they are gauge equivalent because we can, yeah. So that tells you that each double cone geometry is associated with a conjugacy class. Then the integration measure of the double cone is the one induced from the Hart measure of the of SOD comma 1, which can be determined using the Weyl integration formula that precisely gives you this 2 sinh t over 2 that cancel this decaying factor of the observer. Physically, it says nothing but observer. You're addressing the double cone with respect to the observer. So if you were fixing the double cone, yeah, physically just means that. And so after that, if you're going to the microcanonic ensemble by doing an inverse Laplace transformation of this t left minus t right, you obtain this linear integrals. Okay, so that tells you that consider the wormhole geometry. The double cone contributes a linear ramp growth with respect to the clock time t. In particular, it's non-zero. And so that tells you that if you the whole system, if you evolve under the clock time t, have some non-perturbative small probability to return back to its initial state. So you can ask in the above calculation, what about the 1D N configurations? So that's related to Sasha's question, if you can have N observers. And if you put that configuration in, you find that contribution have exponential decay. You can think of is the other matters, the other observers are ordinary matters in the static patch. So those have the same polynomial mode decay. And also, you can ask, what about the Schwarzschild de Sitter double cone? And here, then the isometry group breaks from SOD, 1 to R cross SOD minus 1. And in particular, this measure factor is equal to 1. So you don't have anything cancel with the exponential decay. Physically, that just means you can think about the black hole is also kind of matter excitation in the static patch. And I will tell you that the matter have a polynomial modes decay. So here, this corresponding to the decay of the black hole into the, at least when the black hole is small, such an observer do not fall into the black hole. And you can ask, what about other conjugated classes in the SOD, 1? So here we consider quotient with a boost vector, but you can imagine add rotation. And in general, it's a maximum torus on this group, Lie group. And that you can interpret as a turning on chemical potential in the system. And because in our model, the observer do not have any, is not charged under the rotation. So in the current model, it's insensitive to this angular momentum. But you can try to enrich this model by adding some rotor who's charged under the angular momentum. Then you will, we expect you will find some new contributions. Okay. So what? So far I'm just talking about the gravitational calculation. We can ask, what is the microscopic origin? And so for that, we what is the microscopic origin in terms of static patch de Sitter space? Using the idea that static patch de Sitter is given by the clock union the HDS imposed with the Hamiltonian constraint. Then you can think of the return amplitude we are calculating as evaluating the following quantity. So here H contains the union of the observer and the de Sitter. Now, but due to the Hamiltonian constraint, this evolution, this insertion becomes the insertion of the time evolution of the de Sitter Hamiltonian, whose eigenvalue denoted as a capital E. And when we consider square of this quantity, we are essentially probing the spectral statistics of this spectral density of the de Sitter Hamiltonian. And if you assume this de Sitter Hamiltonian satisfy random matrix universality, this linear ramp is a natural consequence of the spectral rigidity of H de Sitter. Okay. I think time should, oh, I finished earlier. Okay. So let me conclude. We argue that if you consider the inclusion of the observer, then de Sitter gravity naturally admits this non-perturbative small contribution to the return probability. And such a contribution could be understood as coming from random matrix universality of the static patch Hamiltonian. So if this was true, then that suggests that such a wormhole geometry prevents the existence of a perfect clock in de Sitter space. And so if there's no perfect clock that you can measure time, then that indicates that notion of time is not well defined for longer than e to the de Sitter. I'll end here. Thank you.
We have 10 minutes to ask questions. Any questions? No.
maybe naive question. So could another interpretation would be that what you're computing is averaging of an ensemble of clocks?
Averaging of ensemble of what?
Of clocks, of different clocks, and each of them can be an ideal clock, but you have an ensemble of different clocks, and then you lose their orthogonalities.
Ensemble of clocks.
But maybe, sorry, maybe
Yeah,
it
you,
maybe it doesn't
because of the energy constraint,
Okay.
right? So here we put one clock.
Yeah.
But then the clock spectrum, yeah. I think what you have in mind is the following. So we input a clock, then the clock, the spectrum, because of the Hamiltonian constraint, is be given by the spectrum of the H deceder. Now you are averaging an ensemble of clocks.
Yeah.
Little bit hesitate about that interpretation is because this imposing of the Hamiltonian constraint, for me, is only, you can only impose it after ensemble average. Because let's imagine we put a more realistic clock whose instead of have a continuous spectrum but have finite range. Then the clock will have discrete integer spacing. And if you think about a single discrete Hamiltonian, then this Hamiltonian constraint can never be valid, right? Because you have some integer spacing and then some random Hamiltonian, what's the chance that they will meet each other? So here, my interpretation is that you could only impose this constraint at the level of ensemble average. So we're looking at some average system, then we import that. So for the sphere and the double cone, after in this ensemble theory, this clock is constrained. You can import this clock Hamiltonian constraint, right? Yeah, that also brings a very interesting point is that feels like if you trust this interpretation, then the ensemble average is very important in de Sitter.
Because otherwise you never satisfy the
Yeah. You cannot put anything in if you.
Other questions?
Is that the time is now well defined.
Mm-hmm.
So how to understand this fact? So physically or intuitively, do you mean the time has different directions, or just how to understand this illness?
Right. So if you think of time as some physical quantity in the system, then if so, well, those are some speculations, and then so if you think about the time is made out to some degree freedom in the static patch, then its range should be bounded by the de Sitter entropy, e to the de Sitter entropy. So that's a total available state in the system. So that already tell you that there's no infinite time.
Yeah, but we know the notion of time in daily life. This means basically measure, for example, related to causality, for example.
Mm-hmm.
Now, what will happen if you consider there is non particular effect to this time?
Right. So this, right. So maybe it tells you that for a single observer, if it runs very late, much later time, the causality will be violated. It will come back to its initial state. I'm not sure whether that's a violation of causality, but I don't know how to think about. It looks like not quantum mechanics. Mm-hmm. Right. That you can understand it because you have some eternal time, so you can keep track of how the system is evolving, right? But now, if you are living in the decider static patch, instead of trying to probe this, introduce this eternal time as a clock that I put it in by hand, just imagine something that is made out of this decider space, then you don't have this eternal parameter to check the evolution of the system. So I view what I'm calculating is that I'm trying to put like a reference clock which have an infinite entropy into the system and try to prove whether there's a time you can align with. But for a physical system that you don't put it in, then yeah, so that's what I mean. The time of the decider does not exist forever. Yeah.
I guess maybe if you had a physical system, so not only would the energy levels be discrete, but it would have a finite lifetime. So
Yeah.
then they have kind of a finite width too. And
That's right.
Then it's okay, right?
Mm-hmm.
Sort of like, maybe just to make sure I understood, like if you were just doing sort of semi-classical gravity, so you could have a discrete spectrum of E,
Yeah.
and then because H ds would have had a continuous spectrum, and then you can always match any discrete.
Yes.
But because of this ramp, sort of non-perturbatively, you think that there are actually some discrete levels of H de Sitter, then it will match. But I guess if the E's have a width, then it will be okay. So
If E
maybe
has a
that's another
width,
way of saying that the lifetime has to be finite.
Mm-hmm. I more agree with what you said, but I want to. This ramp is not much about the discreteness of the spectrum. It's about spectral rigidity. So the plateau. Yeah. Right. So, but no, we don't have a theory about this plateau. Yeah. It feels like if you go into an alpha state, like let's imagine not putting a Hawking state.
Well, from that point of view, I guess if you only consider the ramp contribution, it would have been okay for E to be discrete, right? Because H still has an integral.
For which?
I mean, in other words, if you're just considering the ramp contribution, the double cone,
yeah,
the E's could have been discrete. It would have still been consistent. Right? Then there's still an integral over the spectra of H.
Well, yeah, after you do the integral, then
After you do the
then you just look at the this tail of the correlation function. Yeah, it will still be okay, but then there'll be higher fractions.
Yeah, I agree.
Yeah. So you are saying that this one is Right.
You were kind of looking ahead to the ramp when you said the E's shouldn't be discrete. I mean, to the plateau.
If you're trying to, I didn't put that in, but if trying to extrapolate. Yeah.
Any other?
Naive question. Maybe previously you have explained you have construct a relativistic particle model and with a clock. So I want to ask, what's the physical consideration here to consider such an action with combine clock and the particle? Because
well.
And why the action for the free clock is like this, not other form of action?
Okay, maybe just here. You mean why consider this action?
Yes.
Oh, that's a particular model we introduced. So in fact, people have considered other models where you just consider import a clock and fix it at the center of the static patch without keep track of the relative direction in the decider space. But you can make it more realistic by asking its position in decider space. So that's what it's just a thing. You can make it more complicated, I think, but I don't think the physics change too much.
Okay,
As long as it does not
in
couple.
this action, so which parts represent the observer for the clock? Or the particle?
So this X represent both X and E. This curly E and curly T represent the observer, but the observer contains two. So X, you think about it's a location of the observer in the Sitter space, and the curly E is a clock that associated with the observer that it's measure its proper time.
Okay.
Yeah.
So when you have more observer for some action, maybe it's also should combine a particle with the same.
You can do whatever you want. You can have another copy of this thing, or you can have some relativistic particle, etc.
And observer is defined in bulk, not on the boundary.
Yeah, there's no boundary. It's all closed manifold. It will change. I mean, maybe let me comment. This whole construction that it's very important that the observer is kind of eternal. It does not talk to the field in the Sitter except this constraint, funding constraint. If you imagine it coupled to QFTs in the de Sitter, then the story will be very different. Because then, then you cannot, then you don't get this linear ramp. For example, a model for the observer you may think of is to put a black hole in the Sitter space. Okay, and actually people think about it. Now, so now this double cone, including the observer, is nothing but this double cone for the Schwarzschild de Sitter. So you can tune their temperature such as their equilibrium. So you get a smooth geometry, but then you won't get such a linear in T ramp. The reason is because the horizon, black hole horizon, de Sitter horizon are talking to each other through QFTs. So in particular, this bulk trace, where it is, this bulk trace, you'll find that the only invariant state is a Hartle-Hawking state. Here, because it's decoupled, then you get a family of state that is a Hartle-Hawking state, then plus the relative time shift of the observer. But in the case with the Schwarzschild black hole observer in general coupled to QRT, those states disappeared. So, but also this Bonham algebra construction, this type 2-1 also failed. So, yeah.
Okay.
Putting a scalar field. Well, you need to tell me what are your conditioning now. So if conditioning a particular excitation of the scalar field, yeah, I haven't thought about that problem. Yeah. Well, for the yeah, it's more. I'm more confident using that to talk about the early universe, where you look at the expansion, the global size of the Sitter. Not, and haven't thought much about in static hash. Okay, thank you.
Okay, time is up. So let's thank the speaker again.